Hi everybody, this video is going to be about atomic numbers, isotopes, and ions. So we already know that an atom has a nucleus, which has protons and neutrons in it. The electrons are on the outside of the nucleus, but this lesson about atomic numbers is going to be looking at how many of each of those particles we have. So when you look at the periodic table, you'll see little boxes like this. The number at the top is the atomic number. That's the same as the number of protons. The number of electrons under normal circumstances would be the same as the number of protons. The atomic mass number you'll find at the bottom of the box. It usually has decimals on it. It's an average. So when we're trying to count how many particles we have, we'll be rounding to a whole number. That's the atomic mass number. It'll be the number of protons plus neutrons. So if you have 6.94 for lithium, you would round up and say it would be 7. This is a mnemonic a lot of people like to try to remember mass minus atomic number equals neutrons. Atomic number is the same as the number of protons and the same as the number of electrons. So if that helps you, great. If not, it's not something I would ever ask a quiz question on or anything. It's just a mnemonic to help you remember. So here's a practice problem. If we have sodium, the atomic number we would find on the periodic table would be 11 up at the top of the box. The mass number, remember we're going to round, so instead of 22.99, it's going to round up to 23. Protons is the same as the atomic number, so sodium has 11 protons. Because you're not told any other information, we can assume that this is a normal situation. So the number of electrons is the same as the protons, so it has 11 electrons. To get the neutrons, we're going to have to do some subtraction. We'll do mass number minus atomic number. And remember, because we're counting individual particles, it wouldn't make sense to have a decimal. We're not going to have 0.99 of a particle. So round up to a whole number. 23 minus 11 gives you 12 neutrons. Now what we're going to do is we're going to look at what happens when we take an atom and we start changing the number of particles inside of it. If we change the number of protons, we're going to get a brand new element with a brand new name. So sometimes you'll hear people say that the number of protons determines the name of the element. The protons is the unique characteristic that decides which element you have. So sodium will always have 11 protons. If it doesn't have 11 protons, it's not sodium. Sodium is the name for the atom that has 11 protons in it. If you took one away and you only have 10, it's not going to be called sodium anymore. Now it's called neon. If we take an atom and we change the number of neutrons, that makes a new isotope. An isotope is just like a version. We might all have cell phones, but the version of cell phone might be slightly different. We might all have cars, but the version of the car is slightly different. So when we change the neutrons, we're changing the atom into a slightly different version of itself. Some are going to weigh more, some are going to weigh less. So an isotope we say is the same element, it's going to have the same name, it'll have the same protons, it'll have the same electrons, but I'll have changed the number of neutrons. To try to describe isotopes to people and to try to tell them which version you have, we write the element name and then we put a dash and then we list the mass number. Now it would be nice if we just put the neutron number, right, since it's describing the number of neutrons, but unfortunately we just don't. We use the mass number. So for example, you could have silver 107 or you could have silver 108. 108 weighs a little bit more because it has an extra neutron in it. So if we have cesium and we have 82 neutrons, we look up the atomic number of cesium on the periodic table and we find that it has 55 protons. When we have the top of our box for cesium on the periodic table, we would see that the number 55 is at the top. So that's the atomic number for cesium. Next, what we're going to do is we look at the neutrons plus protons, add them together, and that gives us the mass number. So we have 82 neutrons, and I know that because the problem told me that I had 82 neutrons. And I add together the protons that I found from the periodic table. That tells us that the version of cesium in this question is cesium-137. Even though the periodic table may say 133, the periodic table just has the most common isotope. It has the most abundant version. The question we had wasn't the most common version. So cesium-133 is the most common in the universe, but cesium-137 may just be a different version that can exist. So when you look at your periodic table, the number you see is an average of every single isotope. We call it a weighted average. We're not going to just add up, for example, for carbon, 12 plus 13 plus 14 divided by 3. What we're going to do is a bunch of math to try to take into account that most of the carbon is carbon 12. So when I look at the periodic table, my average mass should be closer to carbon 12. If I were to take a scoop of carbon up, I would see that most of the atoms were carbon 12, a few of them were carbon 13, and only a couple were carbon 14. So those averages on your periodic table give you a clue as to which isotope is most common. Whichever it rounds to is the most common isotope. Here's some examples of some special isotopes that have special names or special purposes. Hydrogen sometimes has fancy names. You'll see here if we have hydrogen with a mass of 1, meaning it has no neutrons, just one single proton, we call it protium. Hydrogen with 1 neutron is called deuterium. We use this in a lot of our machines trying to figure out the shape of molecules. Deuterium doesn't really show up in some of our machines, and so it's a way to make a molecule look a little bit simpler. We can hide the hydrogens so that we can figure out what the rest of the molecule looks like. Hydrogen 3, when it has 2 neutrons, is called tritium. Tritium is a little bit radioactive, and we sometimes put it onto a molecule so that we can figure out where the molecule goes in a metabolic pathway, or during a reaction, maybe we swap one of the hydrogens for a tritium and see where it ends up. It can help us figure out how the reaction happens. It allows us to trace where it's going. Carbon 12 is our normal type of carbon, but carbon 14 is the kind that we use for carbon dating. So when they're trying to figure out how old a set of dinosaur bones is, for example, they check how much carbon 14 there is, and that can tell them. We'll learn more about that in our next chapter. Some elements have lots and lots of isotopes, and some don't have very many. So it's nothing I would ask you. I wouldn't ask you how many isotopes does lithium have. I wouldn't expect you to know which isotopes exist. I may ask you what the most common isotope is, and you would find that by looking at the periodic table, but that's probably about all I would ask you. So one thing that can be a little bit tricky is there are a couple of ways of writing our isotopes. This way here with the name dash mass number is how I've shown you so far in this presentation how to write the isotopes. But sometimes you don't want to have to write the entire name. It gets a little bit cumbersome. It takes up a lot of space. Sometimes we just want to write it as a symbol. So you can see up here, this is another way that you can write it. You would put the number of protons at the bottom, and you put the mass number at the top. The thing that's a little tricky is that's actually backwards from how it's on the periodic table. On the periodic table, we have the protons on top, mass numbers on bottom. So the easiest way to remember it is the mass is going to be bigger than the protons, right? Because the mass is protons plus neutrons. So it's always big number is mass number, smaller number is protons. So regardless of how it's written, you can always look at the size of the number and you can figure out which one is which. Next, let's look at what happens when we change electrons. So we found out if you change protons, you get a new name, a new element. If you change neutrons, you get a new isotope, a new version. Now, if we change electrons, it's going to be called an ion. Under normal circumstances, sodium would have 11 protons and 11 electrons. If the charge on a proton is positive, that means we have a total of plus 11 here. An electron is negatively charged, so 11 of them would be a minus 11. And if I add those together, they all cancel each other out, and our atom ends up neutral, no charge. So you could say it has 0 charge, or you could say that it's neutral, meaning no charge. But what happens if I take away an electron? I get rid of one of them. Now I have 11 positive from my protons, but now I only have a negative 10 from the electrons. So you can see that if I take away an electron, I end up with a positive charge, meaning I have too many protons and not enough electrons. Sometimes people have a hard time with this because they think, but wait a second, I took away something and I got a positive number. And that's true. We took away a negatively charged object, which left our overall total charge a positive. So sometimes it's helpful to actually write it out like a little addition problem so that you don't get your plus and minus backwards. So let's look at oxygen. Normally we would have 8 protons and 8 electrons. They cancel each other out nicely and we get a neutral atom, 0 charge. But if I gave oxygen 2 extra electrons, now I have a plus 8 from my protons. Now I have 10 electrons and they're each a negative 1, so I get a negative 10. And you can see that they don't cancel each other out perfectly. I have too many electrons this time. So a negative charge means that I have these extra electrons. So I get a negative 2 charge. I like showing this as little pictures. I think when you see the actual objects, you can see how they do or do not cancel out. So for example, if I had 3 protons and 3 electrons, my charge would be 0. So what ends up happening that cancels, that cancels, that cancels, and I'm left with 0. Now what if I have 3 protons but I only have 2 electrons? Now this cancels, and what's my overall charge left over when I took away one of my electrons? Now I end up with a plus 1. There's a proton that does not have an electron to balance it out, so we get a plus 1 charge. What if we had 3 protons, but now I have an extra electron, now I have 4. So this cancels, this cancels, this cancels. Now what's my leftover charge? A minus 1. Now I have my 3 protons, but what if I have 5 electrons? I've added 2 electrons. Now we can see that these cancel and I'm left with two negatively charged objects that have nothing over here to cancel each other out. So I get a -2 because I have these two extra objects that are both negative. So drawing the little circles out may take extra time, but if you're having a hard time getting your plus and minus correct, it might be a good idea until you get a little bit of practice. So next, we're going to look at what we call these negative and positively charged ions. They have special names. So if it has extra electrons and negative charge, we call it an anion. It's like we want to split that in half there. It's not an anion, it's an anion. And if it's a positive charge, we took away electrons. Now we don't have enough electrons to cancel out the protons. We call that a cation. It's not a cation, it's a cation. So you can remember how to pronounce them because we should end each of them with the word ion since that's what we're describing. So sometimes people will say, well, what about if you took away protons? Why are we constantly talking about taking away electrons? And the reason we're talking about that is if we took the protons away, it wouldn't be oxygen and sodium anymore. So the only particle that we change under a normal chemical reaction are electrons. They're the ones that are easy to add and subtract, take them away and add extras. So that's why we're primarily going to be dealing with ions. Changing the protons and neutrons is what happens during a nuclear equation or nuclear reaction. So in our nuclear chapter, yes, we'll talk about that, but that's not the kind of thing you're going to be doing in a normal chemical reaction. Normally, we would be doing things that would change the number of electrons. So ions are really important for the rest of the school year. If you'd like a couple extra videos about isotopes and ions, you can watch these. All right, everybody, I hope that was helpful. Bye.